just to make it clear that there actually are consequences to the mathematic things that I'm saying. Let's look at renormalization in the context of theoretical physics, particle physics, quantum mechanics, all that bullshit, as it stands right now. So a Wikipedia article on renormalization. I scroll down to the first section, self-interactions in classical physics. The problem of infinities first arose in the classical electrodynamics of point particles in the 19th and 20th century. The mass of a charged particle should include the mass energy in its electrostatic field. Assume that the particle is a charged spherical shell of radius r sub e. The mass energy in the field is an equation that has r sub e in the denominator. Thus, as r sub e approaches 0, this becomes infinite. This implies that the point-like particle would have an infinite inertia and thus cannot be accelerated. Incidentally, the value of r sub e that makes the mass equal to the electron mass is called the classical electron radius, which blah 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 blah. Compton wavelength, some other bullshit. Okay, renormalization. The total effective mass of a spherical charged particle includes the actual bare mass of the spherical shell. If the shell's bare mass is allowed to be negative, it might be possible to take a consistent point limit. So they're just making up shit on the hope that it might work. Okay. This was called renormalization, and Lorentz and Abraham attempted to develop a classical theory of the electron this way. This early work was an inspiration for later attempts at regularization and renormalization in quantum field theory. See also regularization for an alternative way to remove infinities from this classical problem, assuming new physics exists at small scales. So you have to make all sorts of wild assumptions, and it's even then, it's not guaranteed that it will yield results that make any fucking sense. But wait, it gets worse. Should I read this? When calculating the electromagnetic interactions of charged particles, it is tempting to ignore the back reaction of a particle's own field on itself. But this back reaction is necessary to explain the friction on charged particles when they emit radiation. If the electron is assumed to be a point, the value of the back reaction diverges. Basically, it becomes infinity. For the same reason that the mass diverges, because you have a fraction with it in the denominator, so as it approaches 0, poof, because the field is inverse square. The Abraham-Lorentz theory had a non-causal pre-acceleration. This is where it gets worse. Sometimes an electron would start moving before the forces applied to it. I'm going to read that again. The Abraham-Lorentz theory had a non-causal pre-acceleration. Sometimes an electron would start moving before the forces applied. Let me go back a little bit. The total effective mass of a spherical charged particle includes the actual bare mass of the spherical shell. If the shell's bare mass is allowed to be negative, it might be possible to take a consistent point limit. This was called renormalization, and Lorentz and Abraham attempted to develop a classical theory of the electron this way. This early work was the inspiration for later attempts at regularization and renormalization in quantum field theory. Now we'll step through there. The Abraham-Lorentz theory had a non-causal pre-acceleration. Sometimes an electron would start moving before the forces applied. What are we doing, people? What are we doing? You made up shit, knowing that only sometimes it might help you, and then, when it clearly fails, you're like, oh, yeah, well, this is inspiration for later attempts. We'll just fuck with it the same way. Are you kidding me? Oi. Now, to be fair, here's the next paragraph. The trouble was worse in classical field theory than in quantum field theory, because in quantum field theory, a charged particle experiences jittery motion. It's in German. I'm not going to say the German word. I'm not, no. Due to interference with virtual particle-antiparticle pairs, thus effectively smearing out the charge over a region comparable to the Compton wavelength. In quantum electrodynamics at small coupling, this electromagnetic mass only diverges as the logarithm of the radius of the particle. Oh, that's better. I mean, it is, but the problem remains. The problem remains. You didn't solve the problem. And you're still just sitting here like, oh, but math must be perfect. Let's trust the math. And this is like supposedly the best tested and most proven accurate physical model that has ever existed, right? The problem is, in order to do this renormalization for the most part, what you have to do is you have to look at the measurements that you've taken, look at the theory that you have, fuck with the theory, fit the measurements into it, and then that's your renormalization. Basically, that's part, because you have to rescale your infinity back down to what you measured, and then you're like, oh, see, it works. Of course, that's always going to match observation, because you're literally just screwing with your equations so that it fits your observation. No level of this is okay. What are we doing? What? And particularly, this is particularly a problem because, where is it? Well, yeah. This is a sign that the point limit is inconsistent. Yeah, that means that your math is not consistent. There's somewhere in here where it notes this. Regularization? I think it was in regularization. I don't know. Somewhere in here it said that, fucking Christ. That it's never been demonstrated that quantum mechanics is mathematically consistent. But people who believe in quantum mechanics will sit there and say that you need to trust the math. Don't go with your intuitions. Your intuitions are trash. You need to trust the math. But at the same time, the math is known to not be valid because we're doing bullshit like this. At every level. What? What the fuck? What the fuck? I don't have a solution for this. I'm not magical genius man that has answers here. But I think it's important to look at this critically and ask, what the fuck? Why does this get a free pass to just do whatever, and then we get to say that, oh, it's the best, most accurate theory ever. It's never been proven wrong. Well, how could you? How could you prove it wrong? Because whenever it comes down to it, you're looking at predicted infinities that you're just correcting away magically. Wait, I remember what this section looked like. I think I can find it. Okay, yeah. Attitudes and interpretations. The early formulators of quantum electrodynamics and other quantum field theories were, as a rule, dissatisfied with this state of affairs. That I can respect, right? Like, sitting there and being like, okay, well, sometimes this works, but this is bullshit. We need to find something better. I can respect that. I'm okay with that. It seemed illegitimate to do something tantamount to subtracting infinities from infinities to get finite answers. Yeah. Freeman Dyson argued that these infinities are of a basic nature and cannot be eliminated by any formal mathematical procedures, such as renormalization. Dirac's criticism was the most persistent. As late as 1975, he was saying, Most physicists are very satisfied with the situation. They say QED is a good theory and we do not have to worry about it anymore. I must say that I'm very dissatisfied with the situation because this so-called good theory does involve neglecting infinities which appear in its equations, ignoring them in an arbitrary way. This is not sensible mathematics. Sensible mathematics involves disregarding a quantity when it is small, not neglecting it just because it is infinitely great and you don't want it. Right. Another important critic was Feynman. Despite his crucial role in the development of QED, he wrote the following in 1985. So this is even 10 years later than Dirac's criticism. The shell game that we play is technically called renormalization, but no matter how clever the word, it is still what I would call a dippy process. I'm not entirely sure what that means. Having to resort to such hocus pocus has prevented us from proving that the theory of quantum electrodynamics is mathematically self-consistent. It's surprising that the theory still hasn't been proven self-consistent one way or the other by now. I suspect that renormalization is not mathematically legitimate. Yeah, it's not. It's not. It can't be. Feynman was concerned that all field theories known in the 60s had the property that the interactions became infinitely strong at short enough distance scales. This property, called the Landau pole, made it plausible that quantum field theories were all inconsistent. In 1974, Gross, Politzer, and Wilczek showed that another quantum field theory, quantum chromodynamics, does not have a Landau pole. Feynman, along with most others, accepted that QCD was a fully consistent theory. Just based on that. QCD has its own issues, completely separate from this, that are clearly issues. Clearly issues. Yeah. Yeah. The general unease was almost universal in texts up to the 70s and 80s. Beginning in the 70s, however, inspired by work on the renormalization group and effective field theory, and despite the fact that Dirac and various others, all of whom belonged to the older generation, never withdrew their criticisms, attitudes began to change. Go kids! Especially among younger theorists. Yeah, go kids! Kenneth Wilson and others demonstrated that the renormalization group is useful in statistical field theory applied to condensed matter physics, where it provides important insights into the behavior of phase transitions. In condensed matter physics, a physical short-distance regulator exists. Matter ceases to be continuous on the scale of atoms. Short-distance divergences in condensed matter physics do not present a philosophical problem, since the field theory is only an effective, smoothed-out representation of the behavior of matter anyway. There are no infinities, since the cutoff is always finite, and it makes perfect sense that the bare quantities are cutoff dependent. Right, but then the problem is, you have to measure that cutoff point. So your equations will always work. This isn't a theory. It's not. You have no theoretical basis for what's going on. You were just measuring it directly and then saying, "Oh, this is how this works. This is how this works." Which that has, that has value. Don't get me wrong, but you're claiming that you have a mathematical theory here, and in the middle of that, you're admitting, "Oh, well, yeah, there's a whole bunch of bullshit we do, but it's okay. It doesn't matter." It predicts things really accurately. But, the problem when it doesn't is because we're dividing by zero and we don't know how to do that because it never occurred to us that maybe we need to develop new math or new ways of thinking about the math that we have. So what we just did is we just waved our magic wands and we took the measurements and shoehorned the measurements in there so that oh, see? It works. What the fuck? What the fuck? This is not going to be something that lasts forever. The quantum mechanical thing, in 200 years, it's not going to still be here. There's not going to still be quantum mechanics. Somebody's going to figure this shit out, and it's going to be this huge, kids at school are going to be taught, like 4-year-olds are going to be taught, oh, look how stupid they were to think all of this, just like it always is. Like, oh, look, people thought that the Earth was the center of the universe. How stupid are they? Haha. Like, it's going to be the same thing here with quantum mechanics, because this is some bullshit. This is straight up actual bullshit. Like, thinking that the Earth is the center of the universe makes infinitely more sense than this. That actually makes sense. This does not. They're literally just making up shit because they don't know how to deal with a division by zero. For one, they're always assuming that it would go to infinity. That division by zero should go to infinity. When a cursory glance at mathematics demonstrates that that's nonsense. That's not how it actually works. That's not what division by zero actually does. And for another, the way that they're correcting it so that it looks like it's good is some shady ass shenanigans. It's like, no. And then, on top of that, they're pitching it publicly as the most successful theory ever. Yeah. It's going to be hard to bring these guys down, but they're going to go down hard as fuck, and they're going to be the laughingstock of scientific history for a very long time. This is going to, when this gets overthrown, this is going to be way, way more mocked than flat earthers. I guarantee it.